Hello, and welcome to the first lecture in this course about the science and technology of graphene. Carbon, the sixth element in the periodic table, is one of the most fascinating elements in the world. It's the basis of life. There are two kinds of bulk carbon crystals, diamond and graphite. We all know that diamond is very precious, whereas graphite is abundant. Diamond is electrically insulating, while graphite can be used to make electrodes. Do you know why they are so different, although they are both made of carbon? The answer lies in their atomic structures. In diamond, each carbon atom is surrounded by 4 other carbon atoms, forming a regular tetrahedron. Periodical repetition of the tetrahedrons in 3D space forms the diamond crystal lattice. Graphite, on the other hand, has a layered structure. In each layer, the carbon atoms are arranged in hexagons. The plane of the layers is called the basal plane, in which each carbon atom is surrounded by 3 other carbon atoms. In each layer, the carbon bonds are extremely strong, even stronger than in diamonds. However, between layers, the bonds, which are known as van der Waals bonds, are weak. This makes graphite easy to flake off and appear soft. Because of this property, graphite can be used to fabricate pencils. Humans discovered graphite at least 6,000 years ago, and it's estimated that the total graphite reserve of the world is around 100 million tons. Although graphite is very common and not very interesting in itself, things happen when you scale down. In the imagination of scientists, one layer of carbon atoms in natural graphite, now known as graphene, has been thought to have amazing properties. For example, the in-plane mechanical strength should be even better than diamond, and electrons are expected to move very fast in graphene due to reduced scattering effect. However, to produce this single layer of atoms on an insulator so that its electrical properties can be measured is extremely difficult. Andrei Gam and Konstantin Novoselov, researchers at the University of Manchester, were among those scientists who were looking hard for methods to isolate graphene. They were driven by the idea to observe the electric field effect in metals, which meant they wanted to change the conductivity by applying an electric field to adjust the electron density. As we know, our modern electronic circuits are based on the field effect in semiconductors. They wanted to observe similar phenomena in metals. However, it is difficult because the density of electrons in metals is much larger than in semiconductors. Imagine when you drink, then the water in your bottle becomes less. But if you take the same amount of water from a lake, you will never notice the change in the water level, simply because there is too much water in the lake. Therefore, one has to reduce the thickness of the metal to reduce the amount of electrons. But ordinary metals will mechanically break before they are atomically thin. So, Geim and Novoselov thought of graphene, which is a semi-metal. They tried several ways to reduce the thickness of graphite, such as mechanical polishing, but could only reach a thickness of about 10 micrometers. Then, one Friday evening in 2004, these scientists decided to use Scotch tape to produce a few layers of graphene. When they had the material, they immediately fabricated some devices and, for the first time, observed the electric field effect in it. 1 year later, the similar effect was observed in monolayer graphene. A few years later, in 2010, they were awarded the Nobel Physics Prize